Welcome back to Trilinos Tips. Today we'll be talking through a sample code of a usage of a Belos GMRES solver, continuing off of our previous episode talking about how to navigate the Trilinos source code directory. So jumping right in, I'm in my top level Trilinos directory. I'm going to cd into packages and then Belos. From here I'm going to go into the Tpetra examples, actually the Tpetra tests, and we'll pick the block GMRES test file. And I'm going to look at this file right in the middle here, test block GMRES with Harwell-Boeing matrix files. That's what the HB is for, Harwell-Boeing. Open it up. And here we are. At the top we have some copyright header code. Here's a brief explanation. This driver reads a problem from a Harwell-Boeing file, and the right-hand side corresponds to a randomly generated solution. The initial guesses are all set to 0, and no preconditioner is used in this case. In our include files, we have some Belos configuration definitions, a Belos linear problem, the Belos Tpetra adapter. This basically tells Belos how to use Tpetra's distributed linear algebra within its linear solver structures, and then the Belos Block GMRES solver manager, which gives the code for the GMRES solver. I'll back up to this one really quickly and show you a little bit more about the Belos linear problem structure. For that, it's appropriate to introduce you to the Doxygen page. Here's the Belos Doxygen page for the develop branch of Trilinos, which is what I'm on. I'll put the link for that down below in the description. And if I want to look at the Belos linear solvers class, I can go here to classes, open the tab for the Belos classes, skim down until we find the Belos linear solvers class, linear problem class, sorry. Okay, here's some Doxygen documentation generated for the Belos linear problem, which again is the header file we're looking at here. The linear problem simply stores the information about the matrix and right-hand side vector that we are looking for with GMRES. You can use the default constructor or pass in your operator A, your empty solution vector X, or it may not be empty, that may be used as your initial guess, and your right-hand side B. Has various set methods. You can set the operator if the operator is changing, set a new left-hand side, set a new right-hand side, mess with the residual vectors, set a left preconditioner or a right preconditioner, and so on and so forth. Tell the linear system whether the operator is Hermitian, and these update solution functions usually get called within the linear solver, some accessor methods, and so on here. You can apply the operator of the linear problem, apply the left preconditioner, apply the right preconditioner, and again, most of these things are called within the linear solver. Usually the ones that you need to worry about are the constructor and then setting the preconditioner further on if you're going to use one of those. Set left prec and set right prec. Okay, so back to the code. This next line here, Tpetra matrix IO, that just allows us to read in a Harwell-Boeing matrix file for testing purposes. The next few of these have some Tehf-ose macros. Yes, that funny name there, Teuchos. It is pronounced Tehf-ose, as if there's an F in the middle of it. That's our tools package in Trilinos. The command line processor helps us to parse various options from the command line. The parameter list, you'll see later, lets us pass parameters to our linear solvers. Standard catch macros is simply because this is a test within Belos, so that has to do with our testing infrastructure. Tpetra core is one of the files that allows us to use Tpetra linear algebra. The Tpetra CRS matrix is the structure for our sparse matrix A that we're going to pass in. CRS is for the compressed sparse row format, which is pretty common. You can look it up on Wikipedia. Okay, we have some using TypeDefs here. Do note that we have this using namespace Tehf-ose, so if there are mysterious commands in this file and you're not sure where they're coming from, they may be coming from Tehf-ose. Don't necessarily recommend that option, but that's what this example does. And here we go down into our main. So again, we've got several TypeDefs. We're pulling a scalar type from whatever our standard Tpetra MultiVector is. This scalar traits class just allows us to set some constants, such as what is the value of 1 with this scalar type, what does the value of 0 look like. Allows us to find a magnitude type, what type of value are we going to hold when we take the norm of a vector. We can tell that to expect, say, positive real numbers. The Tpetra operator, we've TypeDefs that as op. This right here is just telling us what the scalar type is. Could be double, could be float, could be complex. Tpetra MultiVector. And then these next two, Belos operator traits and Belos MultiVector traits. Those again are part of the interface between the Belos linear solvers library and the Tpetra linear algebra that's running underneath the hood. So that operator traits specialization for Tpetra allows us to apply an operator within Belos. The MultiVec traits allows us to do operations with different multivectors, dot products, and such as that. So I'll explain those a little bit more once we get further down the page. Tpetra scope guard. This is standard for whenever you're using code with Tpetra. It initializes Teuchos underneath the hood and sets up your MPI world and all of that. Success of the test will initialize that as false, verbosity initialized as false. Look, we've defined that one constant from our scalar traits up above, my processor ID here. And we'll look at our MPI communicator, that's how you get that from Tpetra. Here we're parsing some command line parameters. Is my process verbose? Am I in debug mode? The frequency, which is how often residual convergence information is printed out to the screen by the solver. Num right-hand size, as it says, the number of right-hand sides we're solving for in our linear system. The block size used by the linear solver, kind of asking how many right-hand sides are we solving for at once. That's not exactly what it is, but we'll talk more about that later. Maximum iterations for the solver to use. If you put -1, the solver will determine that on its own. String for orthogonalization type. This one uses DGKS. That is a variant of classical Gram-Schmidt, which has a heuristic for determining whether or not reorthogonalization is needed. So it has a tolerance built in that you can adjust, and if the orthogonality of your vectors doesn't match this tolerance, then it will reorthogonalize. Other options are ICGS, which automatically does 2 passes of classical Gram-Schmidt per iteration, and IMGS, which I believe the default is to do 1 pass of modified Gram-Schmidt per iteration. File names, so we're going to read in this BCSSTK14 Harwell-Boeing matrix. You can access that on the Sweet Sparse matrix library. We'll start with a relative residual tolerance of 10 to the -5. Again, that MT is one of the TypeDefs we used above for magnitude type. These are options for the Tehf-ose command line processor. So you remember that using namespace Tehf-ose above. This is the Tehf-ose command line processor that we've defined here. And we're setting some options. Do we want verbosity or no verbosity? Do we want debugging checks? How often do we want that solver printing residual information? What is the relative residual tolerance used by the solver? What file name are we looking at here? How many right-hand sides are we solving for? What's the maximum number of iterations that we're going to take for this linear system? What is our block size? What orthogonalization type do we need? We also have an option for TSQR, tall, skinny, communication avoiding QR, if that option is enabled. These lines here simply tell the Tehf-ose command line processor to go ahead and parse these commands from the command line and make sure that was successful. We'll readjust our verbosity parameter depending on whether we've set debug parameters or not. Get my rank from the MPI communicator, just for the sake of not printing messages out on all of our MPI ranks at once. Check if my process needs to be the one printing things out to the screen. If so, we'll print out the Belos version. Okay, here's where things get a little bit more interesting. We'll pull the data from the Harwell-Boeing file and build our matrix. So here we have an RCP to a CRS matrix with a certain scalar type, and we're going to name it A. So let me step through this line here. This capital RCP, again, this is one of those things that's in the Tehf-ose namespace, Tehf-ose : RCP. This CRS matrix, remember, is the Tpetra : CRS matrix. ST was the scalar type we defined above, which is more than likely going to be double. Now, RCP stands for reference counted pointer, which is very similar to the smart pointers inherent in C++. For various reasons, Trilinos has its own implementation of reference counted pointers, and that's what you see here. The capital RCP is the noun, the object, the pointer. Later on, we'll probably see a lowercase RCP. Lowercase RCP is the verb. Take this thing I'm creating and make it into a capital RCP, a capital reference counted pointer. There's a really great guide to Tehf-ose RCPs, Tehf-ose reference counted pointers. I'll link that in the description below. Be sure to look at that if you need more guidance on RCPs. Okay, so here we're just calling the Tpetra function that reads in our matrix A from files. So there's our file name. Again, com is our MPI communicator, reading into this matrix A here. Then we need another RCP, Tehf-ose reference counted pointer, to a Tpetra map. Why do I need a Tpetra map? The Tpetra map essentially tells us how this matrix is mapped against the various MPI processes that we've got running. The domain map says how should we map a vector that's in the domain of a vector that A could be multiplied by. How would that be mapped against different processors? So we've grabbed that out. Here's another reference counted pointer. Belos expects most things to be contained in these reference counted pointers. This is a reference counted pointer to a MultiVector. Again, if you remember up top, we define that to be a Tpetra MultiVector, and Belos knows how to interface with that due to this Belos MultiVec traits. Notice that this Belos MultiVec traits is templated on that Tpetra MultiVector that we defined up here. Okay, so going back to this line here, we've made a reference counted pointer to some empty multivectors, B, our right-hand side, and X. The reason we had to go and pull this Tpetra map was that this map tells us how to create these multivectors X and B, X being our solution vector and B being our right-hand side. So now we'll initialize these things. X equals little RCP of a new Tpetra multivector using the map that we pulled out from the domain map of our matrix A above, and we'll tell it how many right-hand sides, how many vectors this thing needs to have. Remember that capital RCP is the noun and the pointer object. Little RCP is the verb, saying take this thing inside the parentheses and make it into a capital RCP. This multivector traits here, I'll go back again to where that's defined above, but we're calling on these Belos multivector traits this function mvrandom. We're going to randomize the values in this vector X. And again, that was defined up here. These Belos multivector traits, this is defined in the Belos Tpetra interface, tells Tpetra how to interact with Belos. And later on we'll use these operator traits. That's what tells Belos how to interact with these Tpetra CRS matrices. Okay, so we've randomized our vector X. That means we've created a random solution to this problem, essentially. We'll create our right-hand side vector B using the same map as X. A could maybe in theory have a different range map than its domain map, but 99% of the time those two maps are the same, so we're going to create it using the same map. Here we're using the operator traits that were defined above. Again, those are what tell Belos how to use a Tpetra CRS matrix. Here's the apply function we're calling. We're applying the matrix A to the vector x, and the solution is going to go into the right-hand side B. So again, what we've done to set up this problem is we've created a random solution, and then we've applied A to that random solution to create our right-hand side. Note that if you want a more difficult right-hand side for Belos, you can create a random right-hand side B directly. Applying A to a random vector kind of damps out some of the small eigenvalues and makes a little bit of an easier problem with this right-hand side. But in any case, this is how we set it up. And then we'll go reset our initial x, our initial guess x, to a value of all zeros before we start the solver. Okay, now just a few more details about these MultiVector traits and these operator traits. Where did these functions come from? mvrandom, mvinit, and the apply. Let me go ahead and show you that in the documentation. So if we go back to our Belos Doxygen, click on the list of classes again, look through the Belos block, and we're looking for MultiVector traits first. MultiVec traits. This one right here, not the one that says specialization. That's a specialization of these MultiVec traits to an internal Belos MultiVector test class. You want this MultiVec traits here, traits class, which defines basic operations on multivectors. I'll put that link in the description also. So here's our MultiVector traits. These are implemented for Tpetra, for Tpetra, and for Teuchos multivectors. So all of those have an implementation to Belos contained within Trilinos. You're also welcome to write your custom implementation of your custom linear algebra to Belos by implementing these traits. We have various clone functions, which allow you to copy different multivectors. Clone views, which are just taking a subview of a multivector. You can get the global length of a multivector, get the number of vectors in the multivector. Does that multivector have constant stride? Here's the functions we were calling earlier. We were using mvrandom here. Replace the values in the vector with random vectors. We can also use mvinit to set all the values in the vector to a certain value. And then there's various mathematical functions, Belos type functions, except for they're not really Belos because these are occurring across potentially distributed vectors, but Belos type functions that allow you to do dot products and transposes, scale your vector by a constant, add two vectors, etc. Okay, so that's where you can look at the documentation for all of these guys. If we want to look at the operator traits, we'll go back to classes, click down into the Belos, and then where are the operator traits? That's a partial specialization. Let's look at the operator traits here. Okay, so operator traits is a lot simpler. Again, this tells Belos how to interact with an arbitrary operator object. In our particular case here, we're looking at a Tpetra CRS matrix, but that could be a sort of matrix-free operator or a preconditioner object, another solver object within Belos, or basically anything for which you want to implement these apply and apply transpose functions. So again, if you're calling apply through the through the operator traits, your operator A goes in the first argument, then the vector that things are being applied to in the second argument, and the solution vector in the third argument. And then you can specify whether or not you're transposing the matrix A. Okay, back to our code. So again, that's where all of these things come from. These MVT functions called from the MultiVector traits. These OPT functions called from the operator traits. You can go look those up in the Belos documentation. Okay, so we're getting a little bit more information. How many elements are in each of our vectors, get the global length, set a maximum number of iterations if that was set to default. Here's some things with the parameter list. Again, this is a Tehf-ose parameter list, comes from that using namespace Tehf-ose, Tehf-ose .parameter list. We're naming it Belos List. We're setting several parameters. And there's documentation for the Tehf-ose parameter lists as well. I will put that in the description below. Alright, so we're setting the block size, the maximum number of iterations, the convergence tolerance, the orthogonalization that we set earlier. If you want a full list of the parameters that can be passed to the Block GMRES solver, again, that can be found in the Belos documentation. We'll look at our classes. We'll look for our Block GMRES solver manager. That's Block GCR-ODR. Okay, Block GMRES solver manager shows you some inheritance classes, different constructors for this solver manager, set problems, set parameters, and we want to see what parameters this solver has. And they aren't included in the documentation. Oh, there they are. Okay, it's just in the constructor list, not the set parameters list. Here we go. So the parameters that you can pass to the Block GMRES solver manager are listed here. I think these for most solvers are listed in the Doxygen documentation, but occasionally you may have to go look in the solver manager source code to mine that out. That's on our list of things to improve in the documentation front. Okay, so in addition, you can put a maximum number of restarts. You can change the output style of the solver. You can have an adaptive block size, so on and so forth. Alright, so here we've just set all those parameters. Verbosity level. Belos errors plus Belos warnings. Okay, so this little driver is always going to put out Belos errors and warnings. If we're debugging, we'll add this Belos debug. If we have verbosity, we'll add the timing details, the final summary, the status test details, and then we go and pass that into our verbosity level in our parameter list. Now, what exactly are these guys? The Belos timing details, the Belos final summary, the Belos status test details. This takes a little bit of knowing to figure out where these are defined. This is an enum that the solver reads to tell which pieces of information it needs to pass out. And later, in a later video, I'll walk you through actually running this example, and we'll see what those timing details and this final summary and the status test details look like. The status test is simply the convergence test. Belos allows you to set custom convergence tests, so you can check the explicit residuals, the implicit residuals, or set a custom convergence test on your own, and it'll print out those details. Final summary, how many iterations the solver took, things like that. Final timing details, a breakdown of the timing for the orthogonalization, for applying the operator, etc., etc. If you want to see how those are defined, go to this Files tab, and we're looking for the Belos types file. There it is. I think it's Belos types. Nope. Belos types HPP. And right here in this set of lines, this message type. Okay, you can use this enum to figure out what you need to pass your verbosity parameter. These are all in hexadecimal, and you'll see this in certain parameter lists for, say, Teuchos and some ifpac2 drivers. If they just have verbosity equals a number, this is where they're getting the numbers. Okay, so moving on a little further through our example, we've set all these parameters, we've set the output frequency. Here we finally construct our Belos linear problem. Again, that's templated on the scalar type, the MultiVector type, or Tpetra multivectors, and the operator type, which is our Tpetra CRS matrix. We're passing it our matrix A, our right-hand side B, and our solution vector X, which will also be used as an initial guess. In this case, we've set it all to zeros. We set the initial residual vector. That's not entirely necessary. I don't think that makes a difference in this particular problem. We call problem.setProblem. That just computes some initial residuals, gets the problem ready to go. You can check if that happens to throw an error. I don't think I've ever seen it throw an error. That's usually pretty error-free. Okay, and then we can set up our Block GMRES solver. So for this particular example, it's setting up a Belos Block GMRES solver manager. We name it solver. And this is another Tehf-ose function, Tehf-ose ... RCP from ref. That means take this reference. So if you see this problem up here, we're taking this problem and making a capital RCP from it. Also taking this Belos list and making a capital RCP from it. And I'll link that documentation and that RCP Tehf-ose guide in the description below. Okay, so we're calling this thing our solver. Another side note here, if you were wanting to switch between different solvers, at this point you would probably make this a generic Belos solver manager. So spell that all the way out, leave off the Block GMRES, and oops, don't want to insert anything. Leave off the Block GMRES, and then you could create a generic solver from your solver factory. You could pass in the name of the solver from the command line, decide if it needs to be CG, minres, BiCG stab, etc., etc. Okay, here our solver just prints out some statistics. How big is our matrix? How many right-hand sides do we have? And then it performs the solve. Sure enough, I did. Okay, here's where we call the solve. Don't delete that line in your solver or you definitely won't get a good answer out. You have a Belos return type. That's another TypeDef in this Belos types file. There it is, an enum for return type, converged or unconverged. Okay, and that tells you the result of your solver's solve. Now, since this is a Belos test, it actually verifies that the residuals for the problem converge to what they say they converge to. So we're just setting up a standard vector of whatever is that magnitude type for those residuals. Setting up some new multivectors to hold that residual, one for each of the right-hand sides. Remember that map tells us how Tpetra maps the multivectors across processors. And we'll actually apply our operator A to that solution vector, throw it into our new residuals vector, compute the difference. So this is B minus AX. We're actually computing those residuals by hand. Take the norm of that by hand, and then we're going to normalize that by the norm of the right-hand side. So here's a little bit of code that goes through each right-hand side, prints out the residuals for each of those right-hand sides, and then the test determines if each of those residuals actually met the requested tolerance. Tells us whether the test passed or whether the test fails. At the end, these are some Tehf-ose testing statements. Did we pass our Belos test or did we fail? And then we exit success or exit failure. Okay, so hopefully that gives you a better idea of what's actually going on in the Belos code. Next video, we will get our hands wet with this example and show you what the output looks like, maybe play around with some parameters. Thanks for joining us on Trilinos Tips.